Good evening, everyone. We'll wait for a few minutes, okay? And then we'll start today's class. I hope your last week assignment was also okay. Were you able to solve it based on my tutorial? Was it helpful? Do you
I
have
think it's little bit, some questions are easily
some
solved.
question? Some questions are?
Easily solved.
I didn't get it.
Easy, easily solved.
AC resolve. Okay, fine. So if you have any doubts, you can ask me, okay, based on last week's or assignment or this one. So today we'll start with the week 3 class. So we'll wait for a couple of minutes to see if someone else is joining. Okay. Good evening. Good evening, everyone. We'll start the class. So, yeah, welcome to the third tutorial class of the impedance spectroscopy. So, yeah, my name is Sri Lakshmi. I'm a PhD scholar at IIT Madras. I'll be doing the TA session for the week 3 lectures of electrochemical impedance spectroscopy. Okay, so what I'd actually thought was we'll start the class with what most of you had asked last time. That is, you wanted to know how we can plot the impedance or how can we do that in MATLAB. So I thought I'll start with that. But since only 4 people have joined, what do you want me to first give the summary of what was taught and then move on with the MATLAB? I think that will do good because if anyone else is joining, it will be helpful for them as well. If that's okay for everyone.
Summary of what is taught.
Okay, we'll go with the summary first because last time when I did the summary first, some had told they wanted to have the know what how to do the MATLAB. So that's why I asked what do the majority prefer. So okay, fine. So since everyone is preferring the summary first, we'll go with the summary and then yeah, this time actually the content is less, so we'll mostly finish it fast. So then after that, yeah, we can see how to do that in MATLAB. I'll share my screen. Is it visible to everyone? Is it visible? Hello?
Yes, yes, it is visible.
Okay, good. Okay, fine. So we'll start the class from the tutorial 3. Yeah, so first I thought I'll explain the MATLAB question since, okay, we'll keep that for the last. Okay, so summary. So what did we actually look in the last class? Basically, it was the data validation. So in the first class we saw the basics of how the electrode electrolyte interfaces everything, and how do you actually take the impedance value. You need a 3 electrode setup, why it is required we saw, and then we came to a place like how do we plot impedance and everything, how do we represent it, the resistor, capacitor, inductor. We saw everything in first week. The next week we saw how the instrument is behaving. In fact, like how we take it in potentiostatic mode or galvanostatic mode, or then how can we give, is it a single sign or a multi-sign input. How is the equipment giving the sign input, and what is happening. What we are giving is something which is a function of time as the input. That is a potential of current is a function of time. That is EAC equal to EAC naught sine omega t. That is what our input is, either in a single sign format or a multi-sign format. Then what do we get as an output? What we get as an output is something in terms of the frequency. That is the impedance, that is the real and imaginary everything as a function of the frequency. So how that equipment is transforming the time domain values to a frequency domain. So we saw there FFT, then we saw many other techniques like oscilloscope technique, then lock-in amplifier, etc. Yeah, so basically that was what we saw in the week 2. So now the third chapter, I mean the third week, we are talking about, we got a data. Now we want to know if that is correct or not. In the sense, what we need should be something that is repeatable. It should be stable result. That is, when we do the impedance many times, we should have something that is repeatable, stable. The effect of noise should be very minimum, and yeah, we can do it at any amplitude. So how if if we change the amplitude, we are going from linear to non-linear. So we want to know where is the linearity lying, etc. So for that, so these are the basic things we want to know once we get the data. And in order to know this, we are going to validate the data. So for validating the data, we are going to use the techniques like chromachronic transform, the KKT, or a simpler or an easier method of the measurement model approach, or the linear KKT. So basically, there's only this is what we have seen in week 3. Basically, how to validate the data we have got. Okay, so the first thing that we looked into is linear repeatability. So what is repeatability? So any data we get, irrespective of impedance or anything, there can be some error from our part, or there can be some glitch in the equipment or something, or our connections are wrong. I mean, any experiment we do. So we might not get the same thing always. So what if we are doing one experiment only one time? We don't know if it is the correct value or the expected value. So how can we verify that? We can repeat the experiment. So repeatability is to see like if our data is correct, or is that what the system responses all the time. So we have to check into the repeatability. So that is the first thing, checking the repeatability of the experiment, I mean the system. Yes, the next thing is linearity. So we had seen the previous week, like there is a range of perturbation that we can give so that the system will give us a linear response. Can anyone tell me? If anyone remember? Anyone? What should be the input perturbation or the amplitude that we should give for the, if it is a potential EAC that we are giving, that amplitude should have a range we told. So below which it has some issue, above which it will again have some issue. So we had discussed it last week. Anyone knows?
1 to 10 milliwatt you have told.
Yeah, okay, correct. So we had seen, so basically we go for something, yeah, 1 to 10. So we prefer 5 and 10 millivolt. So what does it mean? If we go lower than that, we go lower than 1 volt or 1 volt or below and all, what do we see? That the noise can play a bigger role, and in that case the our reading will have the signal to noise ratio will be poor, and the input, I mean the output that we get will have the effect of noise, so which is not good. Again we saw, so in that region that is less than 1 volt or so, the signal to noise ratio will be low, but still the system will be linear. So we also told that above 10 volt, what happened? Above 10 volt, non-linear effects come to play. So non-linear effect, what does the non-linear effect mean? So above 10 volt, if I go this side, I can say that the non-linear effects come to play and it is undesirable. So how to check which region the system can give us a linear response? Anyone? After 10 volt, okay, not at 5 or 10. What I
High
meant is
frequencies.
high frequency, it will give. So how do we check if the
High
system is,
frequency it will give linear.
sorry?
High
Sorry,
frequency.
not high frequency. What I meant is, sorry, what I meant is at high this potential amplitude, it will give you. So thanks for correcting. Like at higher amplitude, we'll get a non-linear effect. So how do we check that if our system response is linear or not?
You apply the KKT.
Okay, yeah, that is okay. That we do after the experiment. In when doing experiment, how can we say if how can we check if the system is linear or not? Okay, so what we do is, it's a little tiresome process, because what we do is we'll apply different amplitude. That is, first I'll do 5 millivolt. Okay, 5 millivolt amplitude I'll apply, and I'll see how my system will respond. If this is my Nyquist plot, okay, you know it is minus Z imaginary versus Z RE, okay, and I'm getting something of this form. Okay, so this minus Z imaginary. Okay, I'll write it. This is minus Z imaginary, and this is Z real. So first case, at 5 millivolt I'll get a semicircle, any shape. Okay, now I'm applying 10 millivolt. Okay, now imagine when I'm applying 10 millivolt, again I'll get something which is more or less like this within the noise limit. So obviously noise will affect, so it might not be completely overlapping, but somewhere some issue, but still we can say that they both are kind of overlapping. So a linear, so again 5 volt, 5 millivolt and 10 millivolt, I am getting same response. So here I have given semicircle, that means I am taking a simple system. If you are doing with your system, you will be getting different plot. Don't assume that you will always get a semicircle. What I'm meaning is, you are applying 5 millivolt, you will get some shape. You will again apply a higher amplitude perturbation, for example 10 millivolt, you are again getting a curve. Now I'm going for a larger one. For example, if it is 10 millivolt, okay, I'm getting something like this, which is totally different from the behavior which I got in the 5 and 10 millivolt. So you can see that after a particular perturbation, I am getting a totally different curve. So I can say that from 20 millivolt, the non-linear effects are coming to play. I mean, for this case, it might not be 20 millivolt for every system. It differs. I'm giving an example. So how to consider, like when to consider system response as linear? Like what can you do? You can do an experiment experimentally. Data validation is something else. Again, someone told that we can do KKT to understand if the system is non-linear or not. We'll come to that again. At that point, I'll again discuss on that. But just keep in mind that it is not possible for KKT to tell that a system is non-linear in every case. Sometimes the system will be non-linear. Even in that case, the KKT can say it is KKT compliant. Okay, sir had discussed
So
about such.
can we, excuse me, can we say
Yes, sir.
up to 10 milliwatt it follows the linearity, but after 10 milliwatt it is not linear? Can we say like that?
Yeah, that is the basic one. Again, it depends upon, that is the basically saying. So I'm giving you an example. Up to 10 millivolt is what we prefer, we do. But without doing an experiment, I cannot completely tell that yes, it is at 10 millivolt after which non-linearity starts. I'm not sure of that. It might depend upon the system. Okay, but when we are doing experiment impedance, we usually do 5 millivolt or 10 millivolt. We say that above 10 millivolt, we usually see nonlinear effect. Okay.
Okay.
So if you want to know like the exact, so for being on safer side, we'll do up to 10 millivolt. We don't go above that. But I'm telling you, like in order to understand up to which amplitude range you can go, you can do it at different amplitudes and check how your data comes. So where the data completely changes from what you're getting at every other amplitude, you can say that nonlinearity is has begun to be exhibited. Okay, so that's how we check the linearity. So for us to do an experiment, to get a repeatable result, and we prefer to do the experiment in the linear side, right? So something else, when we're doing the experiment, we need to check if the system is linear. Now the next thing is stability. Now how to check the stability? So what does stability means? That is, the system should be stable. That means one system, okay. So this is about the linearity. So I am telling over here the nonlinear effects are coming to play. Now the next case, stability. What does stability mean? I am doing an impedance for one particular material. So what I am expecting is I get a curve like this for my first run. With that same sample, okay, I'll finish one EIS, okay, impedance run. Then I am telling that, or I am expecting that the system will come back to its original state even after doing the EIS. That is, if I run an EIS, I get a curve. I am telling the system is expected to come back to its original state, means again for that same system, when I do an EIS, I should get something similar within the noise limit. There can be some noise limit, so it might not be completely reproducible, but within the noise limit, I should get the same curve again. Okay, that means what I'm doing is I'll do an EIS once. I'll wait for the system. I'll wait for few minutes or something, assuming that my system has come back to its original state. I'll again do. If it is giving me the same curve again, I'm saying my system is stable. But that's not possible. But that might not be possible with every system. There are some system whose the system will it interacts with the solution, or its behavior changes continuously over time. So if there are systems where I do an impedance first time like this, if I wait for 3 minutes and again do, I may get something like this. Something again after another few hours or something I get something like this. So it depends upon system to system. I cannot, stability is something else. That once I apply some amplitude and I get the result, I wait for few minutes or something, assuming that the system, I am expecting that my system should come back to its original state, and I'll again do. If I am getting the same result back, I'll say that my system is stable. Okay, I hope that is clear. So repeatability, linearity, stability. I hope you understand what is the difference between all the three. Now the next, any doubt?
So, ma'am,
Madam,
in
but
the
in this
first graph, we
expression, what
can
you have
say,
given?
Sorry.
pardon me. In the first graph, we can say that it is linearity. In the first graph, you have shown means after a few seconds, if we do the same and if we
No.
get the same curve, that means it follows. It is stability. We can get system is stable. But in the second graph, you can say it is not stable because every time you are getting different graphs. That
Yes,
means it is
correct.
not stable.
Yes, this is not stable. That's what I was telling. If
No,
I'm
whether
not,
it is stability or repeatability.
No, I think, see, when it is changing with that, when it is not changing with the time, that is the stability.
repeatability, when we do, what we do is we
Yeah,
change
Again,
the
in
entire
a
again.
single
system. We change the entire system. Like as far as I do experiment, what I mean by repeatability is I'm studying something regarding, I'm immersing a metal in a solution and I'm doing EIS. I get a curve. I'll change the entire system again. Take a totally different solution. I'll take a different electrode, everything. That means irrespective of, if I take different samples of electrode and the same solution again, if I prepare, there is a repeatability in the way I perform the experiment, so that my system is also giving. Do you get that?
No,
That's what.
I think the repeatability is, see, if you take a similar sample
Okay.
Identical sample with identical solution, and you
Yeah.
repeat the test. You are supposed to get the same results. That is
Yeah,
the
that's
repeated.
what. Yeah, that's what I told now. When I'm doing repeatability, I'll be changing my electrode and the solution. The
Yes.
entire system will be changed. Basically,
The
what I
change
mean, changed in the sense.
with respect to the change with the identical.
Yes, that's what I meant. Sorry if that's not clear. So what I meant is repeatability. See, if I'm, for example, I'm studying how gold electrode behaves in ferroferric cyanide solution. So this will be, first what I'll be doing, I'll be taking one sample of gold. Okay, that will be immersed in a ferroferric solution of particular concentration. I'll do once. This will be my first experiment. Again, I'll take another sample of the same gold. In the sense, I'll be just changing the sample. It will be gold, this is also gold, but it is a freshly polished sample. The preparation, same procedure, I'll repeat again to see that over my experiment, even if I'm doing the same set of experiment the same way multiple times, even if I'm getting the same result or not. Are you getting? So he.
Yes.
Okay, so here again I'll prepare ferroferric cyanide of the same concentration. So basically what I'm doing is I'll first prepare. There can be some error even when we are preparing and also if that is large or not, that error, if I'm taking some measurement, it can go wrong sometimes. So repeatability is something where I'm changing the same sample but I'll be taking multiple times. But when it comes to stability, what we are doing is the same sample, this one, okay, this one I'll run an EIS, okay, this one, then I'll wait for few minutes. The same sample again I'll do, okay. Repeatability is somewhere I'm changing everything. Stability is somewhere the same thing I'm waiting for some time and again doing, taking the reading.
That is the sort of repeatability with respect to time. See, after lapsing some time, if you are able to repeat the results, repeat
Yeah,
the signature, that is the repeat stability of the system.
but we cannot term it as repeatability. What
No,
yeah,
it is with respect to time. There is no
yeah,
change in the system.
yeah, that is what it's meaning, stability. Correct. So, like some electrodes, if I say like magnesium or something, if I put it in water, it will dissolve continuously. So, if I take an impedance once, then after some time, that impedance might not be same. It will not be same. It will keep changing because what is happening, there will be a passive film. You know, magnesium or some alloys, some electrodes like that, will form a passive film. So over time, if I'm waiting for some time, and when I do again, yes, I won't get the same result because dissolution of the metal is happening. So stability is something to understand that if the system can give me a stable, in the sense over time also it is giving me the same result. What we have obtained is actually the impedance, like it is not varying with time or system, or in a better way I can say that after doing the EIS my system has come back to its original state. That is why it is again when I am doing impedance on the same thing, it's giving me the same result. Okay, so that is stability. Now the next thing we should know is causal. So what does causal means? So I'm applying a amplitude. Okay, input perturbation is applied and I'll get an output. So yeah, so I apply an input and I'm seeing how its output is. So when I'm getting the output, I am believing that whatever output I'm getting is solely or it is only because of the input I have given. Okay, there is that is, if I am getting an output, if I get this output, it is only because of input that I have given, that is a 5 millivolt perturbation or 10 millivolt. It's only because of that. That is, there is no effect of noise. The noise is not affecting the signal given, and in that way I am getting a result. That is, my result is only dependent upon my input signal. It has no effect of noise. That is what causality means. Now how to check the causality? So to check the causality, what we can do is we can repeat the experiment. So in order to check the causality, what we can repeat the experiment over the time, and so if there is any noise or something at any experiment, it may come to play. So that's why we do the repeatability of the experiment to check the causality. Okay, I hope these terms are clear. So you can expect one word kind. So some people did ask, there was a discussion about what's the difference between stability, repeatability, etc. So know all these four terms. Okay, you can expect some question maybe in the assignment or the final exam, anything. So these are the four things. Now okay, now coming to the validation. So then we came to the Chronic transform. Why KKT? So I get a data. So in order to check if it's linear or not, it's not sometimes possible. You do the experiment 5 millivolt, 10 millivolt, then again repeat it 15, 20 to check if is it linear or not, or am I getting a different reading. So better there is a like mathematical expression given by which I can check the what to say, the how my results are, like is it linear, stable, or and causal. In order to check that, we use the Chronic transformation. Okay, so we start with the Chronic transformation or the KKT. So what does that mean? For a given set of frequency, I am having ZRE, ZRE value and imaginary value. Okay, so this is what I get experimentally, right? Then what do I do? So Chronic transformation is somewhere where I can first take my the real impedance value and the frequency. Then using the transformation, I'll get the Z imaginary value. Okay, Z imaginary value from the KKT. Then what do I do? I'll compare the imaginary values that I have got using KKT transform and the experimental Z imaginary. Okay, they should be matching. That's first thing. Again, frequency and Z imaginary will be taken, that is the experimental value. Then using the frequency and the Z imaginary experimental value, I'll be calculating the real values using the KKT. I'll then compare it with the experimental values and should be matching. That is how we test the Chronic transformation, KKT. So what does that say? That's what we do. Now what does that say? So if the system is if the system is linear, stable and causal, it should obey the KKT. But these are only sufficient condition. What does that mean? That means if this is that is, I cannot completely rely on that. That is, if a system is linear, stable and causal, it will obey KKT transform. But the vice versa might not be applicable. In every case, we cannot say that if KKT is applied, the system and if the KKT is if the system obeys KKT, we cannot confirm and say that the system will be linear, stable and causal. So it is just a sufficient condition. It cannot be a necessary condition. So basically, we are doing the data KKT for data validation. So, but even if it is validated, we cannot completely say that yes, my system is linear, stable and causal. So that is the general meaning of that. So you should understand, if the system is linear, stable and causal, yes, it will obey KKT. But if I don't know nothing about that system, if I get a graph, okay, if I have an unknown graph, I get that and I do KKT, and if the system says yes, it is KKT compliant, I cannot completely or blindly trust that, because it may flag off. It means it may not obey one or two of those three, but still the system can show it is KKT compliant. Okay, so that's the problem with KKT. One should understand that it's a data validation tool and it is not used to find the real and imaginary part. So as I told, what the system does, if I have the frequency and the real part, it will find the imaginary part and we can compare it with the experimental imaginary values and vice versa. So it is actually used to validate. We cannot say in case if we miss some data, and we cannot use that for finding out the other part. Okay, so that's what we started. That's what we saw first in the initial part of what is KKT. Any doubt? Okay, if no one is having any doubt, we'll move to the next part. Yes. So we said that it's just a sufficient condition, and it's not a what to say necessary conditions. So what are the issues, or in which cases my system can go KKT non-compliant? Okay. So the first case is, can we use KKT for all set of or every type of data can we do, or what are the issues associated with doing KKT? So the first one is the truncated data. So there are cases when we might not have the entire set of data. Entire set of data in the sense, usually for doing KKT, what they say is we should have data over the entire frequency set, that is negative frequency to, negative infinity to positive infinity. That means I should have that much huge amount of data to do KKT, but that is not impossible, right? So how can we decide the like up to like what frequency range I can take the the impedance data to do the KKT analysis? So basically, I'll be doing the impedance for a given set of frequency. So I'll get some curve. If you see, these dotted points are points. So this is at high frequency. I'll start it. So in this region, if you see, the points will be highly crowded. Then I'll get, okay, it's very crowded. Again, it goes to low frequency, and so if you see here the data, even when I'm going further low frequency, I'm still, so this minus Z imaginary versus Z real, I'm drawing a Nyquist plot. So you see here and all data goes like this, and when I come to a high frequency region and a low frequency region, my data is very, very closely packed. Okay. So usually when I'm taking any data for KKT check, how my data should be like this. That is at either ends, my data should be very close to each other. So that region from that frequency regime to other frequency regime, I can take the data. In some cases, if we don't take that into consideration, we have something like this, unevenly spaced data. Again, it is difficult to verify KKT. It may be KKT compliant, but when the system runs, it may say it is not KKT compliant. So we should have, first thing is we should have, so this is how we take the data in the sense, at high and low frequency region is chosen based on the region where we have the very close points. Okay, in between that I need the data. Again, the data should not be so much spaced. Then it might not, even if the system is KKT compliant, it will say that the system is not KKT compliant. So data should be evenly spaced, something like 7 points per decade. Okay, something like that I need. If you're going for something like 3 points per decade, it might flag it off as KKT non-compliant. Is that point clear to everyone? That is, what I meant is the data must be evenly spaced. I should have enough data points, and even at high and low frequency, that points will be very crowded. So I can say that, yeah, even if I take even more low frequency, it should be somewhere around that region. I can come to that conclusion and then take the data. So usually it is preferred that we take the data over the entire frequency region, and the data point should be evenly spaced, and it shouldn't be per decade. I should go for minimum 7 points or something. I cannot go for very low points per decade, then it can flag it off as KKT non-compliant. So we saw some cases. Sir had explained about some cases where the system will flag it off as KKT non-compliant. So first case was truncated data. So here you can see this is the Nyquist plot, and here the open the circles, it is corresponding to the experimental data. So what is happening here in this case? So I have told you I get data from high frequency to low frequency. So here at low frequency, I am not having enough data points. Okay, so so here in this case, it is told that at low frequency, when we go to lower and low frequency, the time that is taken for data acquisition will increase. So based on that, the longer time will be taken, and based in that period of time, if I take longer time, what can happen? The system can continuously change, and also I can have poor signal to noise ratio. So in some cases like that, I might restrict my data to a particular frequency. I will not be going to even more lower frequency. So I may get some curves like this. And for this curve, when I did KKT complaints, what happened? It is flagged as not KKT complaint. So I've also shown the body plot which is showing. So you can see, okay, this is a body plot. You can see the magnitude versus frequency and the phase versus frequency. You see in this region, that is the high frequency regime, I'm getting a good fit. Up to this point and all, I'm getting a good fit, high frequency. When I'm going lower and lower, the fit is becoming very poor. Again, in the phase, it is it's showing perfect over the entire frequency range. So how can I overcome this problem? One way is to do the extrapolation, but still that is not preferred. Sometimes even extrapolation, the data might not be correct. Okay, I can do extrapolation of the given set of data, but again I'm again repeating, my extrapolation might not be done correctly. Again, that might not be how the system behaves. So extrapolation is not that good option, but in case if you don't have data over the entire set, you can think of extrapolation, but again that is not well preferred. What is the best solution? You have to obtain the data at the low frequency and validate without extrapolation. So that is what is preferred. That is, I should get data over a wide frequency range, from high frequency to low frequency range, and also the number of points acquired per decade, should be significant enough. In the sense, I must per decade, I hope everyone knows what is per decade. That is frequency from 0.1 to 1 is 1 decade, then 1 to 10, 10 to 100, 100 to 10 to 100, 100 to 1000. So in each decade, I should have some at least 7 points. If I take the total range as 0.1 to 1000 and I go for doing the acquisition, the equipment can take anywhere in that region. So I might not have points in every frequency interval. So again, that can also cause the KKT non-compliance if you are doing KKT. So what is preferred is, I should have the data at low frequency regime also, and I should try to do without extrapolation. And so in that case, if the system is KKT compliant, it will flag it off as KKT compliant. Is that clear? Okay. Now the next point is unstable system. So is KKT able to flag off the instability? Okay. Yes, the KKT is successfully able to flag off the system as non-compliant if it is not obeying the stability. If it is not stable, it can. So one example that sir had shown about which I am showing is Fe in 1 molar H2OS. So here what happened was, there's an experimental result where the author is trying to input ramp voltage and we are trying to see how the system behaves. So it is told that when no such input of ramp voltage was given, the system will give a correct semicircle. But when I am giving ramp voltage, I am giving another voltage as an input, instead of getting a semicircle at the low frequency, I am getting some behavior like this. So at low frequency, the system behaves differently. That's because of the instability. So basically, the author is trying to see the difference when it gives some ramp input and if it does not giving the ramp input, to understand how if the system is giving a stable result or not. So after that, when KKT was done, so here it is the frequency versus ZRE. So you can see that in this region it is obeying KKT. Now after that you can see the difference. It is not it is not overlapping with our experimental result. So it is real value and the imaginary, both are showing this difference. So again, so if my system is unstable, yes, if the KKT is able to flag off the system as non-compliant. Is it clear? So all these are like one word kind. So you should understand, like, is the system able to flag off the system if it is unstable, or if it is able to flag it off if it is linear? Is it possible in all the cases? You should know that. Okay. So sir, I tried to explain in his lectures through few examples cited from the papers, like if the system will if the software will be able to flag it off as counted or not. Okay, so we saw the case of truncated data and the unstable system. So now the next case is nonlinear effect. So I already told, when I'm changing the perturbation, when I'm changing the perturbation, the system, uh, yeah, when the system is showing what to say, when I'm applying higher potential, uh, amplitude potential, it is possible that the non-linear effects can come to play. Okay, so there's a plot showing the non-linear effect. Okay, and then an impedance was done. Okay, that is so this again you can see that this is at 1 millivolt amplitude, and then I am increasing the amplitude to 300 millivolt. You can see that the system response changes completely when I am increasing the amplitude over here. So I can clearly say that at 300 millivolt, what's happening? The nonlinear effects are coming to play. So it is because of that I am not getting a repeatable result. Okay, just wait a second. I just got it out if I'm recording the video or not. Yeah, I'm recording. Sorry about that. So again, sorry, I'll just again explain the nonlinear effect. I was telling that at higher amplitude, after a point, nonlinear effect will come to play, and I can test that by doing impedance at different amplitude. And in that case, what to say, that the plot will change. It will not be I will not be getting the same plot when I change the amplitude. So here in this case, you can see that at 300 millivolt, my system is behaving as a nonlinear one. Okay, so so in this case, if you see, I'm doing a KKT validation. Okay, so you can see that at high frequency, you can see up to this point and all. Okay, 10 to the 10 hertz and all, it is showing a similar behavior. Again, over here also I'm getting a overlapping result up to a particular at a high frequency I'm getting. But what about going to low frequency? At low frequency, I can see that they're not matching. Here also you can see the difference clearly. So here also at both the amplitude versus frequency and the phase versus frequency, I can see that there is a difference at low frequency. So if the plot of the log current versus potential is non-linear around the DC potential where the impedance data is acquired, then the non-linear effects will also be flagged by KKT. So yes, in some case, so in this case, yes, KKT is able to flag the system as non-compliant. But is that the case always? There are also cases. So someone had told me, I asked initially, can I say that, can I, like I asked how to check the non-linearity. Someone was like, do KKT. But is that the case? Will KKT give me the non-linear behavior? Can KKT flag off the system if it is non-linear in every case? Okay, that is a question. So it may not be. There are also cases when KKT might not be able to flag off the system. So yeah.
Flag of the system, what do you mean by that in a simple word?
I didn't get you, sorry, I did not hear.
Flag of the means, what do you mean by saying
Flag off
word?
means flag off means it will say, like, it will give you a, it can, what to say, it can say, or it can give you confidently say, like, yes, it is KKT complaint. In the sense, flagged means it shows a green signal. It gives a signal that it is complaint. Are you able to understand?
Okay.
Signal, I mean, it's a green signal, like that. Not flag means it's a red signal, something like that. Like a system is can KKT, or I can say can the systems can KKT be used to say that system is linear. I can rewrite the system saying there are also cases when non-linearity is not said, SAID is not said by KKT, or it is not showed by KKT. Okay, in simple words, that's what simply it means. Can it say it is linear or not? Same that meaning. So here you can see clearly when I did impedance at different amplitude perturbation, I am getting a different curve. But when I am plotting it, it is more or less same. So the author is taking it as KKT compliant. So first case we saw truncated data. It may say it is not KKT compliant. Stability, yes, KKT can the method can say yes, it is if it is not stable, KKT will say it is not stable. But when it comes to non-linearity, please keep in mind, it may or may not say that the system is non-linear. Okay, so that is something you should keep in mind. Okay. Now the next thing, we came to a case where we are where it is like the spectrum is showing a negative impedance. So this part is quite important. So there are also cases where when I am doing Nyquist, okay, after some at low frequency, I am getting a negative value. I mean it's going something in the not in the first quadrant, it is here in this case I can say it's in the fourth quadrant, something like this I am getting. So sir had explained with a plot where he told that when I am doing the KKT for this case, I will get something which is a mirror image. I will get something at low frequency because it is going to negative resistance. At low frequency regime, I will get something that is a mirror image. That is, this can be my experimental value, and this is what my KKT software is giving me. Because the real part of the impedance goes to negative value in the low frequency. In the low frequency regime, I will see a mirror image, whereas in the high frequency regime, it will be matching. In the low frequency regime, I can see both will be matching. It will be same. High and mid frequency. So I can see. So when do I see that the real part of the low frequency impedance will be showing a negative value with some DC potential. So when I am applying perturbation and I get a, here you can see the imaginary part is okay. It is a real part which is going to the negative side. So it is in that case, when I do the KKT, I'll get something like this. Okay. So yeah, same thing is written. When the data in impedance form is subjected to KKT, original and the transform data will match well in the high and the mid frequency regime. However, in the low frequency regime, it will be a mirror image. Okay. So how can we do the KKT in this case? The system may be linear, causal and stable, but just because its real part of the impedance value is going to the negative part, just because of that I can see the mirror image. That is, it's not overlapping. But seeing that, I shouldn't say that my system is not KKT compliant. That is, my system is not stable or not linear or not causal. What should I do? The same impedance data, I should convert it into admittance form and then do. And in that case, it is reported that if it's in such case, I should do the data in the impedance admittance form. It will be transformed correctly. So obviously, if my data is converted to admittance form and if it is evaluated and it is KKT compliant, then obviously the data should be KKT compliant. That means, I mean, it is not the issue with the data. So I hope that is clear. So if I am converting it into admittance form and doing the data transfer, doing the KKT, and if it is matching well with my experimental value, yes, then my system is KKT compliant. Is that the only way I can take the data? That is something else to look into. So this is a general statement. If the system is stable in a potentiostatic mode, then the KKT validation must be done on the admittance form. And if my system is stable under galvanostatic mode, then KKT validation must be done in the impedance form. If my system is stable in both the conditions, then I can either go for admittance or the impedance form. So this is just a general statement. You can expect some one word question or something like that. Okay. I hope that
Madam,
is clear.
from the data, is it possible to find from the data whether it is potentiostatic or galvanostatic?
No, you will have to do the data, right? Or either you should try in both the modes and check, and then try to check the KKT. In one case, you are applying a current perturbation and you are getting the potential as output. The other one, you are applying potential perturbation, you are getting a current. So in that case, you will have to do both and check if you are getting the same result or if there is any difference. Then do the KKT and check. That should be the way, I think. Okay. Okay, I'll anyway clarify that. Okay.
One more small doubt. See, if the system is is only stable under potential static mode, no, then KKT must be done in admittance mode, right?
Yes.
If the system is stable only under the potential static mode.
Yeah.
Okay.
Now the next one is some other issues that we can face during the KKT when we are doing. So what to do if the impedance values are very close to 0? So what will happen if my impedance values are very close to 0? Can I do that in admittance form? What will happen? My values are very close to 0 when I'm taking its inverse. That value will be very huge. Okay. Then there are possibility that when I'm doing the KKT, because I'm taking the inverse, values are very close to 0, and when I do the admittance form, it can go to a large value and I cannot be able to check the KKT complaints. So what can be done in such cases? I can add in such a case, there can be large value coming, numerical errors will be associated. To overcome that, I can add a resistance in series so that I am shifting the value a little, so that the value, when I am doing it in admittance form, the entire value will come down and I am able to do the admittance in the impedance in the admittance form properly. Okay, is that clear? So that is one way. Now, so in this case, we saw that if the data is going, the real part is going to the negative value, if I am doing it in the impedance form, it will give me a mirror image. So it is better to perform in the admittance form. So is there any other way to solve it? I can shift the entire data set to a positive value for this case. Okay, and how can I do that? Adding a small resistance in parallel to the impedance data. If I add a small resistance in parallel to the impedance data, yes, then I can verify that data in the impedance form itself. So if I add a small resistance in parallel, I am shifting the data into the positive value, then I am doing the KKT on that on those values in the impedance form. Then if I see that the system is KKT compliant, then I can automatically say that my underlying system or my actual system is also KKT compliant. So that is what it means. Okay, is that clear? So these are basically theory types. So you should understand, like instead of learning it by heart, try to understand what it is. So you
Madam,
don't.
one doubt, madam.
Hmm.
Whether the previous slide now, such scenario can come in galvanostatic study also,
In the sense?
like whether
Oh, okay, like that.
will we get real part in negative if you're doing
Real part can be negative. There are like only I'm not sure, like is
in
it
galvanostatic study also?
I'm not sure. I haven't checked on. I mean, these are all experimental values, so I have not gone through the paper to. I cannot say because I'm not aware of that. I'm sorry. Like either you will have to go through some papers and check because apart from that, I cannot make a clear statement on that. Okay. Yeah. So yeah, then the next thing is the challenges associated in the KKT. So when I'm doing the KKT, what are the issues associated with? The first one is I'll go with the most important one. That is, all these are sufficient conditions and not the necessary ones. So we are actually, we get a data, we are actually doing KKT to see if my system is stable, linear and causal. But if I do it and I get its KKT complaint, I cannot still be sure that if it is non-linear, if it is linear or not. As I've said before, it is able to say my system is stable and causal, but it is not able to say if my system is linear or not. That is an issue. So if we have a totally new system and we do that, it is, we cannot completely rely on KKT and say yes, my system is stable, linear, causal. So that is the main issue. It is just a sufficient condition and not a necessary condition. Now, some other issues are, when doing KKT complaints, is that sufficient care must be taken to avoid numerical errors cropping in. So, as I told, sometimes the impedance value will be very small. So, when I'm doing it in admittance form and all, that is when I'm taking the reciprocal, the value will be huge. I mean, the error associated with that will also be very huge. Okay, so so as I told, one way to overcome that is to add a small resistance in series and do the same step, do the KKT compliance test. So that is one issue. Then the next one is data must be validated in the appropriate form. So as I told, there are cases where we cannot be able to, we won't be able to analyze the system in impedance form, when especially when it's giving in the negative impedance, the real part of the impedance is negative. So one way to overcome that is to do it in admittance form. So we should, or it depends upon being potentiostatic or the galvanostatic mode. Again, so as I told, potentiostatic you should do in admittance, galvanostatic impedance. So that is, yeah.
Sorry to interrupt you. I have one small doubt here now. See, when we are getting the real part on the negative side, one way is to entirely shifting the whole data on the positive side by adding a small resistance in parallel. Now, just now you told that if it is the value the real part value is very close to the zero, then we have to add a small resistance in series. That is correct, no?
Yeah. Okay. That's what. So why are we adding resistance in? Just wait a second.
Yeah, and I got it now.
Yeah. See what
the
yeah.
Yeah.
Yeah. See, if you have something like 0.01.
Yes.
And if you have something sorry. Okay, if I am having some other value, 0.01325, something very big, both will give me totally different value when I take the reciprocal. So like this, if you will, even though you will feel that the values are very close to each other. Okay, so in those cases, if I take the reciprocal and do it in admittance form, the values will be totally different. So that is a numerical error we are talking about. Okay, so in this cases, instead of going for admittance mode, when you're doing that, better to add a small resistance in series, so that these small values can be shifted to a larger value, so that this numerical error can be avoided. That's why we are adding it in series. Adding a resistance in parallel is to shift the values to the more into the positive side. Okay. Yeah, so sufficient care must be taken to avoid the numerical error. Now, the data validation should be done in appropriate form depending upon whether it's potentiostatic or galvanostatic, etc. We know that the conditions are only sufficient. So, being KKT compliant doesn't mean that my system is stable, linear, and causal. In the sense, it can say it is stable and linear, stable and causal, but linearity is again a question mark. That is the next thing. Then another issue. Experimental results suggest that it is always sensitive to presence of noise and instability. So that is also a problem that is associated with the KKT. Okay. Now, what is the alternative to KKT?
One doubt in the parallel resistance. Actually, madam, whatever the negative value, it is experimental data. Negative real party value, it is experimental data. And
sorry, your voice is breaking.
And you have plotted, no?
Your voice is, madam, now? Yeah. Hello? Yeah. Tell me. Hello?
Actually, madam, I always say, hello.
Yeah.
I'll type, madam. I'll type my question. I think my voice.
Okay. I'll just see. So I'll just make it small. Okay. Once you finish typing, you just tell me. I'll check. Okay. Please let me know. I might not be able to see the what to say, the chat box. So please let me know if you finish typing. Yeah. So the next thing is alternatives to the direct integral KKT. So one is measurement model approach and the next one is linear KKT. Okay, what does the measurement model approach do? So measurement model approach is nothing but we are representing the system using passive elements. So like the resistance, capacitors and resistance, capacitors and inductors are used and we are modeling the system using the same system using them, and we say that if the electrical circuit with passive elements can model it well, then my system is KKT compliant. So a measurement model approach is basically fitting the data using the resistors, capacitors, inductors, etc. We'll try to fit the data, and if the system is able to fit well, yes, we'll then tell that it is KKT compliant. So measurement model approach is an alternative to KKT. So how can we model it? So the first one is void circuit. So what is void circuit? Void circuit is something like you will have a resistor in parallel to a capacitor. This is a void circuit. Okay. So what void circuit will have a resistor and a capacitor parallel to each other, and we can have multiple void. So in order to fit the data, we might not be using only one. So basically, the idea is to use multiple void elements and see if the circuit fits well. Now, how do we decide the number of void elements in a circuit? I mean, to fit the data. So what do we do? We will be increasing the number of void elements, and we'll have a data, okay, experimental data. We'll increase the number of void elements and check if the model is fitting well or the fitting is improving. And based on that, we'll calculate the residue value. So the formula for residue is given in the sir's lecture. We'll calculate the residue. So beyond the point, there will be a point when we are adding more of such the void elements. There is no much improvement in the fit. Okay. That is, after adding many number of void elements, the model remains the same. There is no change in the fit. So in that case, what I will do? That is, so I have some data like this. Okay. Using one void element, I am getting something like this. Okay. Again, I will use something. Okay. I am still getting something like this. That's after adding two void elements. This is after adding one void element. So now finally, I've added some uh, uh, three void. Okay. Even after three void element, I'm getting something like this. Imagine. After fourth void element, if I add also, I'm getting the same thing. Okay. There is no change. So that's the maximum fit possible using the void elements. So what can I do in this case? I can plot the residues versus frequency. So if those residues are randomly distributed for the frequency with the noise level, we can then say that it's a KKT compliant. But if I'm getting a trend, okay, if I'm getting a trend in that residue versus frequency plot, then I can say that the void elements cannot be used to fit the given experimental data. Okay, is that clear? Have you finished typing the question? Your doubt? Is there anything in the chat box? Can anyone tell me?
Yes, madam.
Okay, I'll check. How the experimental data will become positive from negative. Okay. Okay. Like imagine what to say. Yeah. So basically it is in parallel. Okay. So I'm just giving an arbitrary example. So if I have to give you an actual example, I'll have to either do some, what to say, calculation and show you how the result will come. But apart from that, I can tell you. I'm adding something in parallel. Okay. So initially, imagine that resistance over there was 5, minus 5. Okay. Okay. This was the initial. I'm just giving a arbitrary example in terms of mathematics, how it is working in terms of mathematics. If you plot and see, you will understand. So my resistance was minus 5, real part. Okay. Now I'm adding a small resistance in parallel to it. Imagine that is something 2. Okay. It is something in parallel. So how will I find it out? Minus 1 by 5, right? To find the resistance. Okay. I'll do this thing. Now when you cross multiply, what will the value be? Is it positive? Is it positive? Is it clear? Hello? Am I audible?
I audible.
Yes.
My doubt is like
Sorry. Yeah, tell me.
whether we have to add this
Add this?
in the experiment, this resistance in parallel.
No. When plotting, when you're gonna give that data to the what to say, KKT analysis, right? So that for that data, you'll have the data, right? So in order to
But that data we are giving from experiment, no?
yeah. So to that data, to the real part, you're adding something in parallel. So
Oh,
basically,
okay. So each and every data we have to add this
yeah, I'll just see if I tell that
in parallel.
see my existing data will be in a negative form, so I can add something in parallel and shift it to a positive value. See what that means is when I'm doing it in what to say, wait, okay. Yeah, so I should add a resistance in parallel and I'm shifting the values to a positive value. Okay. It is not when doing the experiment I'm connecting something in parallel and doing. Okay, that is not what it's meant. Okay, I hope that is clear. Okay, now we stopped it over here. What circuit is consisting of only resistance and capacitance? Okay, so does that mean we can is it possible to model all type of the circuit, like if the circuit has inductance and Warburg? Okay, in the if your circuit representation, if you have an inductor or a Warburg, is it possible to use a void element? Yes, of course you can use, but what is the what should be done? The void element should take a negative value. The data arising from Warburg impedance can be modeled with void circuit with only positive resistance. Okay. So if it has a Warburg impedance coming to play, in order to model using void circuit, I should use only positive resistance. Now when to conclude that void circuit cannot successfully model the data? As I told before, I'll be finding the residue, I'll be plotting it versus frequency. It is required that it should be randomly distributed. If it is having some particular pattern, I can say that it is not this data cannot be modeled using a void circuit. That is what it means. Now, is it only void circuit that I can use to model the data? No, I can also go for Maxwell and the ladder circuit. So, you should know how a Maxwell and the ladder circuit looks like. So, Maxwell circuit is something, I'll have a capacitor and a resistor in parallel. that is similar to void element. Then after that, what happens? I am having multiple capacitor in series with resistor. Multiple such things will be there in parallel to it. It is something like there will be multiple ones like this. Up to n repetitions can happen to model the data. So both are actually same. Like void is complementary to Maxwell like that. So this is the Maxwell. Now how about ladder circuit? Ladder is something like this. I have a resistor and this thing in parallel. Okay, and over here itself I'll have the next capacitor and resistor in parallel. Now again this repeats. This keeps on repeating. So there will be multiple of this kind. They are going on being in parallel. Is this clear? Any doubt?
This is clear, but when we are able to fit with the wide circuit, we should be able to fit it with Maxwell and ladder also, no? Is there a case that where particular circuit cannot be fit in, a particular result cannot be fit with the white and it can be fit with Maxwell and ladder?
Actually, I have not. I have I
Because
think we usually start.
From the sir's lecture, he mentioned that if it can fit with white, then it should be we should be able to fit it with Maxwell and ladder. We may not be able, like
These are
sometimes we may,
actually, yeah, sometimes.
when we would like to interpret our results. See, basically the idea is to once we are fitting all these circuits to some extent interpret the physical phenomena what is happening there. May not be, it's not that we are correctly saying that it is because of this impedance or this this capacitance or this much resistance in series, that is how it is happening. But we should be able to correlate some phenomena in the system with the help of, maybe sometimes it is easy to do it with Maxwell or sometimes with the ladder. We may not be able to do it wide, but fitting as such data, I think it should be interchangeable.
Yeah. All the three are, all the three are complementary, but I'm not sure if because I've not tried fitting till now, so I'm not sure of that. But in the later classes, I think sir will make it clear. I know that all the three are complementary. Okay, like all the three are interchangeable. So yeah, as you told, all the three needs to, should be able to fit the same data. If one is able to fit, it should be able to. Okay, we'll see about this, I think, in the week 4 class, right? So the week 4 is mostly about the equivalent electric circuit. So there we'll be seeing it in detail. Okay, so the point is all the three are like interchangeable, and yeah, so Maxwell is there, ladder is there. So we usually start with the simple circuit models and then we try to fit the data with a large, more complex model. That's how we usually do. Okay, now
can you just go to the previous slide? See, whatever the three four condition you have mentioned, that is applicable only to wide circuit, or is it equally applicable to the Maxwell and ladder circuit also?
Which
let's say let's say we would like to model a data arising from an inductor. So if we should take R and C negative, whether it is with the only void circuit or with the,
that's for the void circuit. So
Maxwell and ladder, whether that also we should take negative value for RC.
No, I'm not sure. You will have to first see in week 4 we'll be, I can explain that in week 4, I think, because when we come to week 4 we will be seeing how these elements are interchangeable, in the sense how each element in Maxwell is related to void, how this capacitor over here can be related to inductor and things like that. So there I think I will be able to clear this. Okay. Yeah. So then the next thing is the advantages of the measurement model approach. So unlike the KKT, I do not need the data over the entire frequency range. It is also possible that even if the data are widely spaced, I can go with MMA. I don't need to go for KKT, because KKT will obviously flag it off as KKT non-compliant if we don't have a data over a wide range. So in such cases, it's better to go with measurement model approach. But as I already mentioned, it is always better that we have the data over a closely spaced set of frequency. Frequency can be widely spaced, but what we prefer is, okay, is to have the data over a closely spaced set of frequency. Okay, so yeah, so that is about the measurement model approach. Now the next one is the linear KKT. So in linear KKT, what do we do is same thing. We are similar to measurement model approach. We are using electric circuit elements. Okay, but the only condition is that there is a restriction placed on the product of R and C. Okay, unlike the other way where R and C can take any value, that is the time constant can take any value, here we are restricting the value. So advantage is that the fit is not required and only a linear set of equations will be solved in linear KKT. So that's how its name comes. Yeah. So now the cases we saw in KKT, how to do if a real part of the impedance shows a negative value. So basically, either I can go for that. So we saw like KKT, if we do, that is normal, the KKT equations, integral equations we take, we saw that we will get a mirror image because of the real part being negative value in the low frequency regime. So either I can do it in admittance form, or I can add a resistance in parallel and do the calculation. That is one way. But another method is, so how to do that in linear KKT and MMA. So if such a data where my real part of the impedance value is negative, and if I'm trying to fit the model using this electric circuit in the sense this void element or anything, equivalent circuits, what will happen? I can get one of the resistance as a negative value. Okay, and at the same time, what will happen? My capacitance will be positive. This based on the fitting done. So this is a theory type. So how it is happening? If you have to see, you have to take a data where the real part is negative. Try to fit it with a model. See if you are getting resistance as negative or capacitance as positive. So this will. So when I am trying to give a physical significance to that, it has no value. Like you're getting a negative resistance and all. So you will say that it's not compliant. But if you are doing this for the same system, if I'm changing it into admittance form and then doing, I can say it as KKT compliant. So how to do this? So same thing. I can add, even if it is equivalent circuit, I can take a small resistance in parallel. So basically that what it means is to the equivalent circuit model that you have got, you are adding another resistance in parallel and you are shifting the impedance value to a positive value. Then so that value will be chosen appropriately based on the negative part of the how much is the value of the negative impedance you have got. Then if the new set of the data is KKT compliant, then I can say that the original data is also KKT compliant. Okay, so this new set of data I can test using linear KKT or measurement model approach, and if that is KKT compliant, original data is also supposed to be KKT compliant. But even after changing if I'm putting a resistance in parallel, and even after doing that, if I get a negative time constant, then I can say that it is not KKT compliant. So even after putting a resistor in parallel, and if I try to find it out, find the fit, and after getting the fit, I find out the R and C and every value. If the time constant is negative, I can say that the data is not KKT compliant. Basically, it is not just about fitting the data using a circuit model. It is about analyzing the value of the capacitor, resistor, everything you have got to see if it has some physical significance. I hope that is clear. Okay, now based on that, we'll see very few questions. Then, yeah, we have some ample time. We'll see how to do in MATLAB. Okay. Yeah. So, who can tell me? Paired response of the system will obey KKT if the system is?
D.
Yeah. So I hope no one has any doubt. We already told it is just a sufficient condition, not necessary condition. That means if my system is linear, causal, and stable, it will obviously obey KKT. But if it is obeying KKT, it doesn't mean the same. So here the answer is all of the above. Next one. If the system response is non-linear, then it is, or it will be, it will not be, it may or may not be. Yes. So we saw, correct. So we saw with an example that if there are non-linear effect, it can in some case say it is if doing KKT can tell you it is not KKT complaint, but that's not the case always. If the system is linear, causal, stable, then it
B will be.
yes. So basically, the first question is if I just changed it and okay, don't get confused. Sometimes this question is kind of tricky. Like if it is KKT complaint, is it so? If it comes vice versa, you should understand that the option changes. Like if it is KKT complaint, it may or may not be linear. But if I say it is linear causal stable, it is KKT complaint. If the system has been unstable during data acquisition, then KKT successfully flags the system as
B.
it will say it is complaint. So it is the issue only with the linearity where it is difficult. Okay. In summary, KKT is a data validation tool is sensitive to violations of, so it is sensitive to violation of causality and stability criteria, but it is not always sensitive to violation of linearity criteria. This should be clear. That means if the system is what to say sensitive to causal or stability behavior, it will be flagged as KKT non-compliant, but linearity it is difficult for KKT to analyze. Just a minute. Yeah, yeah. If the impedance value are very close to zero, the mismatch between the original and transformed data in admittance form can be alleviated by adding a small capacitor in parallel, adding a small capacitor in series, adding a small resistor in parallel, adding a small resistor in series.
Suitable.
Sorry?
D.
D power in series.
Yeah. So the values are very close. Yeah. So you should be very clear. Like when it is negative resistance, what you have to do, real part of the impedance is negative, what you have to do, or when the values are very close to zero, what you have to do. All those should be clear. Okay. For widely spaced KKT method, for widely spaced frequency, KKT method can be used. True or false?
True,
Is it?
because KK,
What is widely
False. No.
false, right? False.
yeah,
Don't get confused. Who is the person who got confused? That's what I was telling. I told you for doing KKT, you need values from negative values corresponding to negative frequency to positive frequency. That is how it is. But how to for that's a for our analysis that's not possible to have values from negative frequency to positive frequency. So how do we fix the region in which we are doing the data? I told you we start from high frequency value. So our value should be such that in that high frequency regime, if I do that, like it should be very close to each other. Here you can see it is very close. Then after that it's okay. Like I can go for something like this. Okay. Again, I'm sorry. Again,
Uh,
in the
just a minute. Can you just go back to just the questions started where you started the question linear KKT related slide. Go back, please.
linear
Previous.
KKT.
Yeah, yeah. So, Next. Yeah, frequency can be widely spaced. I think this got some confusion. That is for MMA only.
Okay, this is MMA.
Yeah, maybe there.
Okay, this linear KKT, both are different. So basically,
Yes.
in all this, you are taking electric circuit. The other one, you are actually using a mathematical equation to solve.
Yes.
So basically, I told you for mathematical equation, you need frequency range from negative infinity frequency to positive infinity frequency. But it is not possible for us to have the reading for all those. So how do you choose for the frequency range? What to do? If I take the frequency range, I need to know the what is the starting and the final frequency, the low frequency and the high frequency. So after the high frequency regime, the points will be very closely packed. Okay, that point should be taken as your high frequency. Again, in the low frequency region also should be such that after a particular frequency, your data will be very close to each other. Okay, so that should be taken as your low frequency regime. Even in this regime, when you're taking, it should be such that your frequency should be such that you should have at least 7 points per decade. Okay, that is necessary. So fixing the initial and final frequency such that at those sites you should have the points very close to each other. Okay, so that's how you choose the frequency. So yeah, so widely phased frequency points cannot be subjected to KKT, because it can sometimes say that it's not KKT compliant. So in that case, you can either go for a measurement model approach. Okay, if the system is stable under potential static mode, KKT validation can be done on which mode?
Admittance mode.
Okay, it is admittance.
Admittance mode.
Admittance mode.
Yeah, it's admittance. So, so this you can write the full. Yeah. In order to check if the system is causal, we have to check the
Stability.
Linearity.
anyone else? What is causal?
Sorry, repeatability.
Okay, someone told linearity. Let me explain once again. So what is causal? Causal means I am applying an input perturbation, I get an output. So I am telling that my output is solely dependent upon, I am assuming or I am considering that my output is totally dependent upon my input. It has nothing to do with the external noise. The external noise signal is not affecting my input signal, and it is having no effect on my output. So how do I check if my system is causal? What can I do? What does linearity do? Linearity is nothing but I am changing the input perturbation value and checking after which perturbation that I am getting a totally different curve. So I can say after that perturbation, the non-linearity effects are coming to play. That is what is linearity and non-linearity. Stability is what? Stability is I am inserting some metal or something in a solution. I am doing impedance with an assumption that my system should come back to its original state after EIS is done. That means once the system comes back to original state, if I again do impedance, it should give me the same result. So stability is something which I am doing on the same thing again and again. So causal is something that means I am saying that there is no noise. Noise effect is nothing. There is minimum noise, nothing, no effect of noise. My signal is totally dependent, output is totally dependent on my input signal. How do I check that? I'll repeat the experiment multiple times. That is, I'll be I'll be disassembling my system. I'll be again connecting it, again applying a potential. So if I'm getting the same result again and again, for the like I'm repeating the experiment and checking if my results are same, I can say that yes, that output is only because of my input and it has nothing to do with the noise. So here I'll be checking the repeatability. Yeah. So this portion was actually very small, like very few questions can be expected. So basically it is like you will have to know how, if it is truncated data, and then you will see if it's stable and if it's linear, if or non-linear, will the system be, if KKT can detect it. Then you will see measurement model approach, what is it, how is it different from the KKT, and yeah, some case you'll add resistor in parallel, some in series. Which case is that you'll have to know. In which case you will do it in admittance mode, which mode you'll do in potential static mode. So I mean admittance form in which case and impedance form in which. So such questions you should actually understand how the system will behave. Then it's easy for you to understand. Okay, so that's all about today's this. But yeah, so many had asked me how to how to plot this in what to say MATLAB. Okay,
Siri, one
just
question here.
yeah.
So that assignment also, if the frequencies are in 3 frequencies per decade in logarithmic, which system is not suitable? Measurement, linear,
That's your
and all that.
assignment question. I cannot answer.
So for
So
logarithmic, what would be the procedure for logarithmic frequencies?
see,
How we have? Yeah.
logarithmic
So.
frequency. What does that mean? Is see
Mhm.
the frequency range we usually say point anything. I'm giving you an example: 100 kilohertz to 0.1 hertz or something. So
Right.
so they are actually spaced logarithmically. And how do we take the data? I told a term. And I also explained what that term is. So I will not say that because that's an assignment question, but I have indirectly given you a hint. If you see this, I will be anyway uploading. I cannot give you the answer for the assignment question, but I have given a hint on what it is. So either you can see the video once again, but I will not say because that's an assignment question. Okay, that's why I'm not answering that question now. Okay, might be in the next
Okay.
class I can tell you. Okay.
Okay. Okay.
Yeah. So yeah, this is the question. How can we plot this in MATLAB? So basically, this is what is like equivalent circuit model. You're using a resistor, capacitor, and in parallel and everything. You'll get a model. So basically, your measurement model approach is also something where you're using combination of void these models and all. So something like that. So how can we do it in MATLAB? So your first step will be you will have to simplify it and you will have to find out the imaginary part and real part as a function of the frequency. So how is it? Anyone willing to try? I am not interested to directly show the solution. So I can tell you the steps by which you should do that. Okay. So your step 1 will be as usual. We have done this in the first class. What do you do? Anyone?
We have to calculate the impedance in the real and imaginary. That
Yeah.
formula.
Yeah. So basically the only difference is that time when we did the numerical problem, I had already mentioned what is a frequency, or I said this is the frequency. So you can obviously calculate the omega value as 2 pi f and you substitute. Here the thing is
Right.
you want to get a impedance data, which is nothing but you have my minus z imaginary versus z real. Okay, and this graph changes as the omega value changes continuously, right? I mean as the frequency changes, my curve will keep on changing. That's how we'll get a curve. So basically what I'll do is I'll find out the expression for z imaginary and z real as a function of omega. That is, I will not be substituting the value of omega, I will not be giving, but I'll get, basically it will be something as a function of omega. You will write an equation for both. Can you try? I've also given the solution value. What you can do is you can substitute other values and find out what is the equation for minus z imaginary and z real. I can give you a few minutes, then let me know. Might be 5 minutes. Please try that. So here I have already told the solution resistance, or you can just write as R1, that is equal to 10 ohms. I have not put the unit. And the parallel resistance is having some value 50 ohms. And yeah, CP value is 30 into 10 to the power minus 6 farad. Can anyone tell me? Please solve it. Tell me what is Z real and minus Z imaginary. So what is the first step? I can find out what is the resistance. So for that, I mean, what is the impedance for this parallel circuit? How will I do that?
1 upon CP plus 1 upon RP.
Yes, 1 by the impedance due to capacitor plus impedance due to RP. Now, what is impedance due to capacitor?
30 into 10 to the power minus 6.
No. You cannot substitute this value directly. That is the
1 by J
capacity.
omega c.
Yes, correct. That is ZC. Don't get confused. This is the capacitance value. This impedance. Both are different. What is the impedance due to capacitor? That is 1 by J omega C. This C value is what is given as Cp.
Here.
Okay. So substitute it. Okay. So you'll get the impedance for this parallel circuit. Please try doing.
We can use the total impedance direct formula, real and imaginary.
Yeah, you can use.
That okay.
I was just showing. Okay, 1 by 10 and this 13 to 10 to the power minus 6. Okay, I'll write this as RP. Basically, what I'll prefer is you can do as how you want. You can put this as CP, RP, etc. just as variables and find out what is the impedance. That is, I'll get something like RP. Let us say P. You'll get something like this. Okay, and then to this you will be adding R solution. So now I have to simplify it. How will I simplify it? I can multiply it with the conjugate, that is RP. Now why I am not substituting the value? I am just keeping it as RP or CP. Why? Because when I am gonna do the coding, I can keep it as such as RP or C and all. Then I'll plot one. I want to change some value and see how that affects the my plot. So basically I can learn more. Instead of plotting it multiple times, I'll get a general equation and then I will change the value and see how it varies. Yeah. So now the total this thing will be R solution plus
R1 RP. That is
okay.
RP.
Okay. I was just writing.
So we can separate that imaginary part in the minus.
Yeah.
So RP upon 1 plus
So RP
upon divided by 1 plus.
sorry, I did not get. What are you telling now?
Now I am telling the real part. Total impedance is R0.
Okay. Okay. RP upon CP, right?
Okay.
RP, right? Correct only, right? RP J omega CP multiplied by, okay, wait, let me just then simplify it even more further.
Yes.
That I think that is better. Yeah, RP CP. RP Cp j omega by RP square plus omega square Cp square.
Right.
Is it correct? Did I make a mistake somewhere? 1 by j omega Cp plus 1 by Rp. Hey, I made a mistake and no one actually corrected me. What is 1 by Zc? It's j omega Cp, right? It's not 1 by.
Mm-hmm.
It's not clear? See, I'm taking this in parallel. So what it should be? 1 by impedance of the parallel is 1 by Zc plus 1 by Rp, right? Now what is Zc? It is 1 by j omega c. So when I'm taking this in parallel, it should be j omega Cp, right? Reciprocal.
Right.
Plus 1 by Rp. So this formula is wrong. Please try. Then I'll discuss. Please do it on your own. Then I'll also discuss.
Is it Rp upon Rp j omega c?
It is j omega c plus 1 by Rp is equal to the parallel resistance, right? So when I take the Z parallel, will be nothing but 1 by the C plus 1 and Rp goes up. Is it correct? Is it correct? I think it should be correct. So we've already discussed this in the first class, okay? Now, okay, 1 by j omega c plus 1 by Rp, if I take Rp j omega c plus 1 into Rp, okay? Then again, same thing as we did before, we'll take the conjugate on both the sides. So if I take that, it becomes Rp.
That is correct. That
Right?
is correct.
Okay.
Right.
So Rp, you'll get j omega
So
Cp.
final, yeah.
Yeah. So
Final
okay.
will,
Since we are running out of time, I'll just write this and stop over here. In the sense, I'll
sure.
go directly to the code. So and you'll get 1 plus. Sorry, j won't come. You'll get something like omega square Rp square
C square.
C square, right? And you will also have a plus R solution value. Okay, then you will have both the real part and the negative part. You will have to separate and write. That's your job. So you will get the equation. So by
Yes.
I wrote in term of Rp and everything is because it will be easy for you to what to say. It will be easy for you if you want to change the value and check how it changes. Now I am going to this code. So code, how will I do? So I am assigning the values, that is R solution values assigned, Rp values assigned 50 ohm. Same thing as we did here. I have done. I am giving a frequency range. This is a frequency. So basically my expression is in terms of omega, right? So this omega value keeps changing. So the next step is to write the same thing. That is, for each value of omega, what will happen? I'll calculate the same equation. I'll be calculating the real part and the imaginary part. Okay. So I'll put that in a loop so that for different value of omega, the value of real and imaginary part will be calculated. Okay. Then what happens is, I'll calculate the magnitude, which will be the absolute value of z real plus j into z imaginary. The face value will be nothing but tan inverse of imaginary by real. That's clear, right?
Yeah, it's clear.
Yeah. Then after that, the next step is simple. You just have to plot. So if you want the Nyquist plot, you can plot the real versus negative imaginary. Okay. Then again, if I want what to say, the Nyquist, the body plot, I will be plotting the frequency versus z magnitude and z phase. And if I run the code, I'll get a body plot. Okay. Okay, so here I have actually plotted it. So actually you should plot it with respect to frequency. I have done that wrong. Then again z imaginary versus z real. Get a curve. So it's simple. All you have to do is you have to you have to plot it with respect to you have to change the frequency, and you have to change the frequency value, and you will have to generate the code for the real part and imaginary as a function of frequency, and then from that you will find out the magnitude and phase. Okay. So that's about plotting and finding it out. So yeah, the next thing is that I want to say is, you get the curve. Okay, you can in fact get some impedance value plot, and then you can actually use some software. Okay. And then try to fit that and check. So one software so many softwares are available online. So one which I could find is about a linear Kramer chronic validity test. You can just plot some, or even your the value that you are simply developing. You can do some simple. You can develop some values using you can develop the values using MATLAB. You can have a small random circuit, sometimes a capacitor and resistor in parallel, and you have some resistor in series. Then you can you can run this code similarly as you run. If you run, you can then save the data. Okay, if you save the data, you will get those points. Then if you are putting into a system and checking, you can see if it is fitting well or not. Are you able to get that? So if you guys are interested, for your next class, you can just try downloading some software which is available online, and then we can just discuss on that also. How about that? After our usual class, we can, if you take few minutes, we can discuss on that also. So you'll understand how you can use the online system to see if the system is linear or non-linear. So if you have some experimental value, it will be that good. Okay. Anything to tell?
Ma'am, can you plot this Nyquist plot curves in Excel?
Nyquist plot in Excel, but the issue is Excel will be even more difficult, right? In the sense you will have the square root. I mean, here you have the your impedance value keeps, your frequency value keeps changing. Based on that, you can do, no problem. But you will have such CP square, RP square. This is a simple circuit. But instead, if you are going for a more complex one, if you are going for a more complex one, it will become difficult, right? You can do it in Excel, but it is more time consuming. If it is MATLAB, or you can even go for any other coding. If you are comfortable with Python or anything, you can do in that also. Basically, I am comfortable with MATLAB. That's why I showed you in MATLAB.
Yeah. Actually, ma'am, I'm not used to MATLAB. One of the software that we have tried was Origin software,
Okay.
and rather than now we are also trying to using Excel. So that is why I'm asking you whether without the
Origin is used for plotting, right? This is before plotting. You should what you're doing. So what did we develop? Like we got Z real and Z imaginary as a function of omega, right? I mean, as a function of frequency, right? So yeah, so we got that as a function of frequency. Now we have to plot that. So in Excel it is possible. So the case is, understand the logic there, that is, or how we are trying to approach the problem. We'll keep changing the omega value, that is, or we keep changing the frequency value, and correspondingly what happens, that omega is a variable which is 2 pi f in that system, in that equation. So that keeps changing continuously. So based on that, the MATLAB is actually plotting that. That is there. So in origin you can only plot any set of value. Either you can go for your Excel, that is also okay, but Excel is even more, it will be time consuming because you'll have this square and all. For simple system you can go with Excel, that's okay. But when you go for if you have a system where if you do the equivalent circuit and you get something to the power 3, 4 and all, it becomes difficult, right? So that is the problem with Excel.
Okay.
Yeah. Anything else? Okay, if nothing else is there, we can wind up today's class. That's all for today. Yeah, so yeah, I hope with what's taught today, it will be easy for you to do. So yeah, the person who had doubt regarding that frequency, just again, if I had talked about some about frequency, you can just repeat the video. I'm not saying it in again because that is like I'm helping you with the assignment, which I don't want to do. But I have given you a hint. Okay. So we
Okay.
can
Thanks.
discuss about that in the next class if you want. Okay.
Sure.
Okay. Thank you, everyone.
Thanks.
Okay, we'll meet the next Tuesday. Thank you.
Okay. Thank you.
Thank you.
Yeah.